Okay, so in section 3-1, we're looking at example number 2 now, and we're using the Haber process as our reversible reaction. You can see the double arrow, and that's indicating that even though we're going from reactants to products, when we get too much products, it's going to start making reactants again. So this is an industrial process, and we've talked about it in Chem 1. And this is one of the things where ammonia is really important. We use it a lot in farming, especially other industrial practices, cleaning products. So we have to figure out how do we take these and make as much of this as possible. Because when you make too much of this, it starts to break up back into these pieces. So we get some other information. It has a equilibrium constant of 140 at 800 Kelvin. Equilibrium constant, no units. So that makes it kind of nice. The first thing, write the equilibrium expression for the reaction listed above. The equilibrium constant expression. So let's pause, get out your formula sheets. I want you to put your eyes on this so you're aware that it exists. So on the front side of your AP formula sheet, if you look at equilibrium, it's got KP and KC and KP right here. And it even has this hypothetical chemical reaction. And so all we have to do when it says write the equilibrium expression is follow this format. And it's telling me that Kc equals products are on top, those are C and D, reactants are on bottom. So just going off of my formula sheet, here's how we would write it. So I have one product, it is NH3. We're using Kc, so it has brackets. Its exponent is the coefficient from the chemical equation. So we have concentration of NH3 squared on top. And on the bottom, we have the reactants. Concentration of nitrogen. And this is to the first power. I'm just going to leave off the exponent. You can put it on or you can leave it. Times the concentration of hydrogen to the third power. So when it asks you for something like the equilibrium constant expression, unless you're 100% sure on it, it never hurts to at least glance at it. Remember, products are on top. Kc uses brackets. In the next couple of questions, we are basically rearranging the equilibrium constant. So this is a reversible reaction, and so we are considering this reaction. We basically flipped it around. And so it wants to know, write the equilibrium constant expression and find the value for each of the following equations. And so what we're going to do as we look at this first one, we're going to call it Kc prime because we already have a Kc. And so we want to label it, just make sure it's a little bit different. So the equilibrium expression for Kc prime, what's that? Oh, not that. It's going to be upside down. Look, your old reactants are now the products. Concentration of nitrogen to the first power, concentration of hydrogen to the third power over the reactants, concentration of ammonia squared. So here's what it says. Find the value for each of the following equilibrium constants. Now, we don't have numbers to plug in, as in we don't have the concentrations. Exactly. So we know the old Kc, and so our Kc prime is going to be Kc to the negative first. Basically 1 over the Kc that we had. Because all we did was flip this upside down, and so we're flipping Kc upside down. So for this one, it was 140 over 1 when the ammonia was on top, and now it's going to be 1 over 140. Or you could say 140 to the negative first power. Your calculator has that button on it. And so you end up with 0.0071. Question 1 on the problems is this kind of thing, where they give you a reaction, they give you a Kc, and they want to know if we change the reaction a little bit, what happens. So, looks like everybody's working ahead of me anyway. All right, so in this next one, all of our coefficients are multiplied by 3. In Chem 1, I would tell you have to reduce. In AP Chemistry, when somebody writes it like this, they're trying to tell us something. And in this case, we're looking for a new equilibrium. And look, the effect that it has on the equilibrium expression, it changes the exponents. And so there is some sort of importance here. And so Kc prime prime is really Kc to the third power. Right? Yeah. So your Kc prime prime is 140 cubed, which is a big number. 2.7 times 10 to the 6th. So far, we've not talked about what the equilibrium constant means. So basically what happens is this constant tells you, is this reaction going to tip towards the products, or is this reaction going to tip towards the reactants? The products are on top, and this is a really big number. And what these two things tell me is that most of this reaction is going to be towards the products. So the products are favored when the number is very large. When the number is very small, as in this last one, 0.0071, product is favored, or excuse me, the reactant. It's a flipped reaction. So when we're making ammonia, most of the reactants want to be products. We have a big number here. When you reverse it, yeah, more on that to come. Our next reaction. So This one is really about as hard as they could have made it. But if you follow the same process, it shouldn't get too bad. Page 2. Did we work ahead of the point where we've already got it? No. So we want to know what is the equilibrium constant expression for this reaction. The products in the reaction as written, nitrogen and hydrogen. Nitrogen to the 1/2, hydrogen to the 3/2. Reactant on bottom to the first power. So what all did we do to the original equilibrium constant to get to here? So we did two things. First off, we flipped it upside down. So it's going to be to the negative first, or to the negative something. And the other thing is we divided everything by 2. And so it ends up being times 2 Kc to the negative 1/2 power, compared to the original formula here. And so 140 to the negative 1/2, 0.085. In this reaction as it's written, what is favored? Are we favoring the products or are we favoring the reactants? The reactants. We have a K value of basically less than 1, tells me that the reaction wants to point this way. Example 3, consider the following reactions. And we're given 2. Barium fluoride, 2 hydrogens, or excuse me, I'm skipping ahead. Barium 2 plus, fluorine minus, HF, H plus. So you have 2 reactions, and we have their Kc's. Both of them are at 298 Kelvin, so we're basically going to leave the temperature alone. Write the equilibrium constant expression and find its value for the following reaction. Barium fluoride plus 2 hydrogens. You have barium ions plus 2 HF. So we have to look at a few different things. First off, what is the equilibrium constant expression for reaction 1? All right, so let's pause for a second. Is yours different than mine? So here's what's going on. Your reactant is a solid. I didn't write it here, but it's a solid, which means its concentration doesn't work in terms of everything else. When it's a solid, we leave it out of our equilibrium expression. So it would be over BaF2 if it were aqueous like the other ones, or gases. KC for reaction 2, they are all aqueous, and so they will all go into the equilibrium expression. Concentration of H plus, concentration of fluoride over concentration of HF. So we want to know about this reaction. First off, we're almost on through finishes. Does anybody need to go real fast? Okay. So the equilibrium expression for this, concentration of barium, concentration of HF squared, and concentration of hydrogen ion squared.